Last week, Google did something no other FANG monopoly had the balls to do. They dropped a frontier-level model with a true Apache 2.0 license, meaning you can finally print cash without a billionaire's legal team breathing down your neck. The release is Gemma 4, and it comes in a few versatile sizes. The heavy hitters are a 31 billion parameter dense model and a 26 billion parameter mixture of experts, or MOE, variant. These models hit intelligence benchmarks that put them in the exact same ballpark as 600 gigabyte monolithic beasts, but you can run Gemma 4 locally on a standard consumer RTX 4090 GPU. This is a sharp contrast to the pseudo-open models the industry usually serves up, models bogged down by restrictive commercial licenses that treat you less like a developer and more like a cloud computing sales lead. This chart shows the brutal reality of local storage. To get Kimi K 2.5 off the ground, you're looking at a 600-plus gigabyte download. Gemma 4 achieves comparable reasoning with a footprint of just 20 gigabytes. And despite that tiny file size, running it locally yields a highly usable output of about 10 tokens per second. A model scoring this high on the Arena leaderboards shouldn't be physically capable of running on local hardware. Google didn't get there by brute-forcing server racks. They got there using deep mathematical witchcraft. To understand how they did it, we have to look at the absolute bottleneck of local AI deployment. If you want to run an LLM at home, upgrading your CPU or chasing higher GPU clock speeds is a waste of time. Your ultimate enemy is memory bandwidth. This diagram shows the physical limit of how fast data can travel from the VRAM, where your model lives, to the processor actually doing the work. Every single time a model generates a token, it has to read through a massive volume of weight files. Generate a word, read the weights. Generate another word, read them all again. Some computer processes are compute-bound, meaning they require intense mathematical calculations. Large language models are severely memory-bound. The math is simple. Moving the data is the nightmare. You cannot physically drill a wider memory pipe into your consumer graphics card. So to hit usable token generation speeds, you have to mathematically shrink the weight data itself. Enter TurboQuant. It sounds like a marketing buzzword for energy drinks, but it's actually Google's highly effective new approach to quantization. Normally, quantization presents a strict trade-off. You squish a model's file size down to save VRAM, and the model instantly suffers performance loss. TurboQuant changes that trade-off. Neural networks traditionally store tensor weights on an XYZ Cartesian grid. It takes massive spatial memory. TurboQuant abandons this, compressing data into a flat circular polar coordinate system. The exact same information is now stored using just two metrics, a radius and an angle. Because these angles follow highly predictable mathematical patterns, the model no longer has to calculate typical, expensive normalization steps. It can just skip them. Before standard data compression even occurs, abandoning Cartesian coordinates drastically reduces the base memory overhead of the entire model. But that's just the surface. To really understand the compression, we have to plunge into the math, specifically the Johnson-Linden-Strauss transform. An LLM's architecture is a high-dimensional space.
We aren't talking about 3D or 4D. We are talking about thousands of interconnected dimensions representing complex linguistic relationships. The core function of the JL transform is to take this impossibly complex high-dimensional space and brutally crush it down into an extremely low-dimensional representation. Vast arrays of complex floating-point values are crushed down to single sign bits, reading exclusively as positive or negative 1. Yet, even crushed to 1-bit values, the mathematical distances and relationships between the original data points remain perfectly preserved. Which forces you to wonder if our human consciousness is just a low-bit quantization within a higher dimensional simulation we lack the hardware to perceive. Anyway, back to the AI models. This precise mathematical transform is why a tiny 20 gigabyte file retains state-of-the-art reasoning capabilities, instead of immediately hallucinating into oblivion. That explains the big models, but Google also released the E2B and E4B edge models. The E stands for effective parameters, and they use a different architectural approach. Standard transformer architectures often struggle with a specific bottleneck, the monolithic embedding block. A traditional model generates one massive contextual embedding, dragging that heavy block of information through every single neural network layer. This creates massive overhead,
forcing the hardware to carry data through layers that have absolutely no use for it. Google bypassed this drag by introducing per-layer embeddings. Instead of one massive block, they act as custom mini cheat sheets, handing tiny, tailored data packets to each individual layer. Contextual information is injected precisely at the mathematical moment it is useful, and completely ignored when it isn't. By utilizing layer-specific cheats, an effective 2 billion parameter footprint outputs outsized intelligence while preserving your RAM and battery life. Because of this extreme efficiency, the E2B and E4B models thrive completely offline on mobile hardware, running natively on Android phones or a Raspberry Pi. They feature a massive 128K context window natively on the edge, meaning you can pass entire code repositories or massive documents right on the device. Gemma 4 also ships with native support for function calling, giving the model the ability to interact with external tools and APIs autonomously. Add to that native structured JSON output, which guarantees the model formats its answers perfectly for reliable parsing and software pipelines. When you combine a massive local context window, function calling, and guaranteed JSON structure, a standard workstation becomes a fully autonomous local agent, capable of executing complex workflows without a round trip to the cloud. Developers can already prototype these agentic flows today, directly inside Android Studio using the ML-Kit GenAI prompt API. By escaping the memory bottleneck through deep, complex math, developers are finally untethered from corporate API rate limits. You own your data, you own your infrastructure, and you achieve true digital sovereignty over your AI workflows. This has been the Raw Deep Tech. Thanks for watching, and I will see you in the next one.